Everybody, here's your review for chapters 12 and 14, last two chapters here in mechanics. In chapter 12 we looked at static equilibrium, and there was really just two rules we needed for static equilibrium. We needed the sum of our forces to equal 0, so the object didn't accelerate linearly, and we needed our torques to add up to 0, so the object didn't start to angularly accelerate or rotate. So we looked at many different examples, levers, bridges, sines, and did all the forces in the x, y, even the z direction should cancel, and making sure your torques cancel as well. One thing that we had to note was the center of gravity of objects, knowing where gravity pulled on, say, a long bridge or a ladder, and in that we find the point where you can push upwards equal to the force of gravity straight down and make the object balance. So mainly that center of gravity coincides with the center of mass of the system, but sometimes it's a little off-centered. So make sure that you pick your pivots when you do your torques so that you can eliminate the forces you're unsure of, and don't forget about the weight of the ruler, the sign, the bar, whatever that object is has a force on it, and if you don't pivot at the center of gravity, you're going to have to worry about that in your torques. Remember that counterclockwise torques are positive while your clockwise torques are negative, and just make sure you sum everything equal to 0. 14, we went to simple harmonic motion. When we started off with springs in series and parallel, so the spring force was given by the minus kx, the restoring force, trying to bring the spring back to equilibrium, and the k can be the effective k of two springs tied together in a series or next to each other in parallel. We said when they were in parallel, you just really have to add the two k constants together, and when they're in series, you can add them as 1 over each other to get a lower k constant than a single spring. So then we looked at a mass and spring pendulum, or a mass oscillating on a spring back and forth, and we have the equation here as x equals the x max cosine omega t plus that phase constant. The phase constant is just how far you've been shifted away from starting at amplitude. So you can be shifted by any fraction of pi as you move around the unit circle. And omega, remember, is measured in radians. So this is the one time we needed our calculators to give us radians for our trig functions. So when we do that, we take the derivative of position. Position should give you velocity, which means you got to do chain rule for that x equation. And velocity gives you a omega sine omega t, the negative sign, and then acceleration gives you the negative a omega squared cosine omega t. So we graphed that out multiple times, talked about where the object was at different moments in time, and what that omega was. We call that omega our angular frequency, and for a mass spring system, it's equal to its spring constant over the mass that it's shaking back and forth. And since we then know that, we can then find the time period, which is the time for the object to oscillate once, or we can find the frequency in hertz, so how many cycles per second the object moves through. We looked at energies in the oscillation, both potential and kinetic energies. If it's a spring system, it's easy. It's just a spring energy of 1/2 kx squared, and turns into kinetic energy at the equilibrium point, back to potential energy, and that oscillation goes back and forth through its motion. So the energy, the total energy you put in the system will remain the same unless there's damping. Then we looked at string and mass pendulums and physical pendulums, and we looked at oscillating when we pulled them back and having gravity try to bring us back to an equilibrium, and found out that the angular frequency for string and mass is just the gravitational acceleration and the length of the pendulum. That's how we made our fun pendulum wave. And again, we can find time period and frequencies, and you can see TP over there is the time period for a pendulum. That's the length over gravity. And the TS is the time period for a spring, which is the M over K. For physical pendulums, remember that there was mass all the way through the pendulum. It just wasn't sitting at the end point. And with a physical pendulum, you have to look at the torque about the center of gravity divided by the moment of inertia of the object. So where it's pivoting from, how easy it is to rotate that will give you the angular frequency. The vertical springs, the only thing we added to the vertical springs was that the force of gravity was in line with the spring force, so you have to incorporate that when you're trying to do your simple harmonic motion. So gravity can get you to an equilibrium point, but if you stretch beyond that equilibrium point, then the object will start to accelerate. We talked about damped harmonic motion, which is the motion when the amplitudes will die off as time goes on, and it doesn't follow the simple harmonic of a cosine omega t for your position. It was that a e to the negative t over tau cosine omega t. So it gets a little more complicated when friction and damping are involved, but knowing that the amplitudes die off at a particular rate and the energies will fall off is important for that section. So there's chapter 12 and 14. That is the end of your mechanics section. Hope that helps for you, and good luck studying.